Thank you. Dr. Solomon, Ivan.
So can you share your slides, please?
Yeah, I'll share. I'll share.
Yeah, please.
Can you see the screen?
Yeah, that's fine. Can you kindly make it full screen?
So yeah, yes, I will do full screen.
Yeah, fine.
Now you're able to see, right?
Yeah. Perfect.
So
yeah, please go ahead.
Moving on today's quantum illumination with classical light. So I'm from IIST Trivandrum, and so I do basically quantum optics, quantum information, and such stuff, and a little bit of optics experiments. Okay, so let us move on. So this is the brief outline of the talk. So first I will discuss the illumination problem, what it means in the quantum mechanical sense. Then some tools which we will require, like, so we need this idea of distinguishability of quantum states. So some formulae I will introduce, and then basically, this whatever this talk is based on some particular examples of Gaussian states and Gaussian channels. So I will introduce this idea of Gaussian states and Gaussian channels, then briefly discuss this idea of what is called as quantum correlation. Then I'm going to examples which basically illustrate, that you can perform illumination of quantum illumination with correlated but non-entangled states. So this section will outline several examples, and then I will go on to some this in continuous variable theory. So we have this idea of phase space displacement, and I'll briefly discuss how this affects our discussion, and how it matters to the examples that we consider. And finally I will end with some concluding remarks. Okay, so this is the brief outline of the talk. So let us move on. Okay, so this is the illumination problem. So imagine so a state rho tilde A is sent. Okay, so your basically light is sent, and you describe that light through a density matrix, say rho tilde A. So you want to know the presence or absence of a target. So you assume that some target was present. Now that target can reflect that light, and then what comes back to you through that reflection is say phi of rho tilde of A. So by phi, what we mean here is, so let us go below here. So phi denotes basically the action of a quote unquote what we understand as a channel in quantum mechanics. In real world, it means say propagation of light through atmosphere, reflect off the target, and reach back the sender. All of this put together can be described quantum mechanically through, say, effectively through a channel, a phi acting on rho tilde of A. Okay, so now, so this is the first. So that means it's a straightforward situation. So rho A was sent. If target was present, phi of rho tilde A is returned. Now, in the second situation, if the target was absent, so rho tilde is sent, but target is absent, so you don't have the object to reflect that light. So what you get back instead is channel action on the vacuum. So in quantum mechanics, we have the vacuum state, which is non-trivial. So what we get back is nothing but the channel action, or whatever, atmosphere, reflection, whatever, acting on this vacuum state. Now, if we are able to distinguish between, say, what is say phi of rho tilde of A and phi of rho ground or phi of vacuum, then we can readily infer the presence or absence of the target. So this is the idea in the illumination problem. So this is very simplistic. So this is what I call as scenario 1. Okay, very straightforward. So rho A is sent, target present means phi of rho A is rho tilde is returned. If target absent, phi of rho vacuum is returned. And if you are able to distinguish between these two different states which can be obtained, then we infer the presence or absence of the target. Okay, so now this is scenario 1. Now, now let us go to the n copy limit. So if you have n copies of the sent state, so you have the state rho tensor n, rho tilde tensor n sent, then target present, then you get phi acting n times on the n tensor state, and similarly in the absence of the target, phi of n of rho tensor n of the ground state is returned. And if you're able to distinguish between, see, phi tensor n of rho tilde tensor n of A and phi tensor n of rho tensor n of ground state, then we can infer presence or absence of the target. So it's a straightforward extension of the single copy elimination problem to the n copy limit. So this is scenario 1. Now in scenario 2, consider the following thing. So imagine you possess a state, a two-mode, a bipartite state, for instance, rho of AB. Now what you do is, so this is some light in, say, two modes of radiation. You only illuminate the target, say, with the A part of that rho AB. Now, if target is present, what is returned to you is, there's nothing acting on B, channel acting on the A part of rho AB. That is what is returned. Now, in the absence of the target, what is returned is phi tensor identity acting on the vacuum tensor rho B. Rho B is nothing but the partial trace of the A side on rho AB. Okay, so this rho B part is with you. Rho vacuum is what is in the background, and what is returned to you is phi tensor I acting on rho ground tensor rho B. So if you are able to distinguish between, say, this phi tensor I rho AB and phi tensor I rho ground tensor rho B, then the presence or absence of the target can be inferred. So you please note here that B part of rho AB is retained by the sender. That means that part is kept with him. Also note that rho AB initially could be entangled between the A and B modes. Okay, so this is the scenario 2. Now, in the n copy limit, you extend the same thing. So wherever there's phi tensor I, replace it with the tensor n, then rho AB tensor n, and likewise for the absence of the target, you have phi tensor I tensor n acting on rho ground tensor rho B tensor n. And if these two states can be distinguished, presence or absence of target can be inferred. Okay, so now I want to highlight one important reference. So this is in a PR that appeared in 2008. So they studied this particular comparison between scenario 1 and scenario 2 in the n copy limit. So what they assumed was rho AB was assumed to be two-mode squeezed vacuum, which is by definition two-mode entangled, bipartite entangled. Then rho tilde A. So scenario 1, they substituted for A as rho tilde A, which was assumed to be the coherent state, which is classical by definition. And to make the comparison legitimate, so they assume that rho A is equal to trace, the partial trace rho AB with the partial trace on B side has the same energy as the coherent state rho tilde A. In this manner, they compared the two-mode squeezed vacuum with the coherent state, that is scenario 1 with scenario 2, and they showed that, scenario 2 can be advantageous with regard to scenario 1 in the n copy limit, n tending to maybe say 10 power 3, 10 power 4 copies of that order. The distinguishability, for instance, of these two states is, or in other words, I should say, these two states are easily distinguished in comparison to, say, these two states. That was the essence of their work. So now, in what I'm going to talk today, so we consider this modified scenario 2. The only requirement change we have is that instead of saying that in the previous, in the original work, they compared a coherent state with one mode of a two-mode squeezed vacuum and demanded that the energy of this coherent state was equal to the partial trace of that two-mode squeezed vacuum state. Instead of that, say, let us assume that rho A was nothing but same rho AB. You take the original rho AB, but rho A is nothing but trace B rho AB. That means in the scenario 1, rho A, which is trace B of rho AB, is used. In scenario 2, rho AB itself is used. And we can have rho AB to be quote unquote correlated, quantum correlated, maybe entangled. And then in this manner, the advantage is the following, that we compare a state with itself between scenario 1 and 2. So this is the definition which we will be using in whatever follows. Okay. So now let us continue to the next slide. So let us now here briefly recollect what it means to distinguish two quantum states. So the idea is basically if you have two states, rho A and rho B, you are allowed to perform POVM with operators, POVM operators E0 and E1. You get two outcomes depending on what state was there available. And of course, you have pi 0 and pi 1 to be the initial probability of, say, generating rho A and rho B. Then you calculate this error probability through using this POVM to distinguish rho A and rho B. So it's a straightforward calculation to show that this minimum error probability is given by this expression, where this this norm is whatever trace square root of A dagger A, which is a trace norm. Now I will recall some very important limits which were obtained earlier in another work. It was shown that this P error minimum is lower bounded and upper bounded by this Q, or Q by 2 rather, and lower bounded by 1 minus root of 1 minus Q square by 2, where Q is defined through this QS, which is some infimum of trace of rho power S of A and rho power 1 minus S of B. So you have to basically take rho A and rho B, calculate their powers, fractional powers, and then you take the trace and then infimum of all the S, and then if you're able to find that Q, then that gives through these expressions we get a lower bound and upper bound on the error probability in using this sort of a POVM to distinguish rho A and rho B. So this this lower and upper bound is called the quantum Chernoff bound, and we can set without loss of generality that initially that two states rho A and rho B are produced with probability half. And then in the n copy limit, so they have this, we have this expression. It comes out to be straightforward. You calculate Q in the single and you calculate power n by 2, and whatever. You replace the Q with the Q power n, and we recover the n copy limit bounds on the error probability. And then, since this optimization is a difficult task, a weaker bound is obtained by setting S equal to half, which is known as the quantum Bhattacharya bound. So all of this work is actually found in this 2007 PRL by Ordonat and other people, where they describe the discrimination problem in very great detail. So we will be using this lower and upper bounds in whatever follows. So now let us go to Gaussian states. So Gaussian states are continuous variable states. So their characteristic function, you know, trace of rho is a state. You take this operators xi and xij, which are nothing but the mode operators like xp, x1, p1, x2, p2, and so on. You calculate, the first order displacements, then the centered quadratic moments with respect to rho, which is by definition Gaussian, defines the variance matrix. And importantly, this variance matrix satisfies this uncertainty principle, v plus I omega by 2 greater than 0, where omega is defined as this, and sigma 2 is the second Pauli matrix. So this uncertainty principle, turns out to be necessary and sufficient to describe a Gaussian state. So the idea is, for a Gaussian state, everything, all you need to know about is contained in this second moments, basically. Okay, so that's what defines a Gaussian state. And okay, so now let us go to Gaussian unitaries. So if you want Gaussian states to get mapped to Gaussian states, you operate them through what are called as Gaussian unitaries. These are characterized through some, as what are called as symplectic transformations acting on the variance matrix. And that you are doing a canonical transformation means that this S omega S transpose S to omega. That means omega has to be preserved under such S, and the unitary itself is characterized through S. And these kind of unitaries map Gaussian states to Gaussian states. So some known results in this regard is that you can always find a S. Say for instance, an N mode Gaussian state, you can diagonalize it using an appropriately chosen canonical transformation, such that you get this diagonal matrix. Note that these things come in pairs: kappa 1, kappa 1, kappa 2, kappa 2. Basically, these are the variance matrix entries in its diagonal form. So these constitute the variances in the canonical quadratures, like some canonical Q1, P1, Q2, P2, and so on. And basically, if you write the corresponding state down, this diagonalization basically factorizes out the state into product of say n thermal states, and in the fog basis each thermal state can be described by through this expansion in the fog basis. And this is the connection. So this is the thermal parameter lambda. So if you have kappa coming in phase space, then lambda is defined as kappa minus 1 by kappa plus 1. So basically, given a Gaussian n mode Gaussian state, you can diagonalize it into a product of n thermal states, each thermal state which is diagonal in the appropriate fog basis. Okay, so now some important definitions. If you calculate the, if you're able to calculate eigenvalues of the given variance matrix, if say you're able to get the minimum eigenvalue that turns out to be less than 1, then the state turns out to be classical, quote unquote, in the sense of Professor Sudarshan, ECC Sudarshan. Okay, so, and then another observation is that, okay, if you have 2 mode Gaussian state, you check for this kind of a modified uncertainty principle, where you conjugate the given variance matrix by this operation T. T is basically 1, 1, 1 minus 1. And then if this uncertainty principle, modified uncertainty principle is violated, then we know that the given 2 mode state is entangled. And then using the eigenvalues, the symplectic eigenvalues of this V tilde 2, you can define logarithmic negativity, which is quote unquote a measure of bipartite entanglement of that 2 mode Gaussian state. And basically kappa tilde, which is the is a minimum symplectic eigenvalue of V tilde of 2, the 2 mode Gaussian states variance matrix. And basically you follow this procedure. Basically you can choose the S to diagonalize that this V tilde 2, which is a modified V2, and then this minimum symplectic eigenvalue, take the log of that, and that gives a minus of log of that. You get a measure of entanglement. Okay. And now going on to Gaussian channels. Basically, Gaussian channels are physical processes that map Gaussian states to Gaussian states. In other words, so if you have some characteristic function, say for example, one mode Gaussian state, then the output state, if you take the state and you have applied it through phi of rho, quote unquote phi of rho being a channel, then a Gaussian channel is particular, then this characteristic function undergoes this transformation. And then in particular, for example, if you have a single mode Gaussian states, V1, it's very easy to check from this relation. You can verify that it undergoes X transpose V1X plus Y. Basically, X and Y, this 2 cross 2 matrices X and Y characterize the Gaussian channel. And we have a channel, quote unquote, means it's a physical process, demands that this sort of a relation, uncertainty relation, is satisfied by Y and X. And this omega is the same omega which appears here. This omega. Okay. Now you can think of action of a channel on one mode of an n-mode state. Then what happens to the characteristic function? So basically, you carry out the operation, whatever we discussed in the first few slides, one mode, one side action, channel. Essentially you carry through, and basically in the variance matrix, it just, the X acts only on the first mode, for instance, and the Y just adds the noise to the first mode. Okay, so this is the action of one-sided action, means you have a noisy channel acting on one mode of a n-mode Gaussian state, then its characteristic function undergoes this transformation, and variance matrix undergoes this transformation. So a particular example of a Gaussian channel is the noisy attenuator channel, whose X and Y is defined as in this manner with okay, so I should have put, I think this, I should have called this A, I called it A, so it should be N. This noise factor is greater than 0 and kappa less than 1. And this channel, sort of describes, by and large, you can model, the propagation of light through atmosphere, and, basically quantum noise can be effectively modeled through this particular Gaussian channel, which is nothing but the noisy attenuator channel. So there are several other channels which I am not going into. This particular fellow is important because it is very, practically relevant. Most of practical physical processes are modeled as this Gaussian channel. Okay, so with this at the background, so let us go to now, distinguishing or calculating the error probability for, say, we are given two n-mode Gaussian states. Our goal is to find expressions for this error minimum or lower bounds and upper bounds on this, this probability, error probability. Okay, so basically, okay, so this, so we have a lot of, involved piece of algebra, which I don't want to go into. So you have to diagonalize, you have to calculate the, since you have rho A power S, rho B power S, that has to be done in phase space. The equivalent has to be done in phase space. So you diagonalize in phase space, then you put the scale factors, so on and so forth. So all these things are available. So the lower bound, what I want to say here is that the upper and lower bounds can be, for two n-mode Gaussian states, you can, easily calculate out the upper and lower bounds on the error probability. Okay. Through this, and all of this is worked out in this important paper by, Perendora and Lloyd. Seth Lloyd in this physical review A paper, which is published in 2008. Okay, so this is the idea is we can actually calculate out this QS using this formula. And here you can note, okay, so I've introduced something called phase space displacement, maybe which I will come later. Okay, so the distinguishability also depends on, importantly, on the variance matrix as well as the relative phase space displacement of the two Gaussian states which are under consideration. Okay, so with these remarks, so let us go to quantifier of quantum correlation. So So what is the idea of a quantum correlation? So as I understand, so if you have a row AB, so in this present slide, I have defined C to be AB. So if you have a row AB, any state that is not of the product form, row A tensor row B, is quote unquote quantum correlated. So that's the idea. So, these measures, mutual information, the need to mutual information, and there are several others. These sort of, capture this non-productness of a given two-mode state. And, there is something to that, say state may be separable, but need not be of the product form. So it can be non-trivially correlated. That means if you calculate out this quantity, this one-dimensional entropy of rho A and one-dimensional entropy rho B and subtract it with S of rho AB, you get, non-trivial, non-zero. You can check easily that, if you rho A and rho B was rho C equal to rho AB was of the form rho A tensor rho B, then this is essentially zero. So yeah, so in this sense that this mutual information captures is a non-productness or the quantum correlation in a state. So you can extend this, instead of using one-dimensional entropy, you could use, for instance, Renyi entropy, and you get Renyi to mutual information. Okay, so this we will use these two definitions in our work for the simple reason that for Gaussian states these are easily calculable. Okay, so now, so what we are going to do is now we're going to consider examples. So let me go back to the slide scenario 2, which is so this is what we're going to do essentially. So we have a couple some joint state rho AB. A part is sent. What is returned is this fellow, and the problem is essentially distinguishing between these two scenarios. And the question is, if rho AB is correlated, can it be advantageous in comparison to only sending, say, for instance, rho tilde A? This is our goal, and you don't need to even rho you need not be entangled. So we all needs to be have some sort of correlation. So that is the idea. So let us go to the example one. So what is that we do? So in optics we have this device called a beam splitter. Basically, it is a very passive device. It's just a glass with a layer of metal, basically partially silvering one side, and half the light transmits, half the light reflects. And so basically what you do, so suppose you are able to make a two-mode state just by you take vacuum, take a thermal state, you pass it through a beam splitter, which is characterized by this unitary transformation. Of course, theta basically specifies reflectivity, transmittivity. So you get a two-mode state, and this beam splitter is a passive device. It's, you don't need to spend any energy on it. It's just a glass, partially reflecting glass. So if you make this two-mode state, you can verify that this is not of the product form. So you're basically you take a thermal state which is highly mixed, quote unquote, you couple it to the vacuum, and you mix it using a beam splitter. So now going into phase space representation. So it happens that you have this on the variance matrices. The characteristic function undergoes this kind of a transformation, and this resulting state variance matrix is given by this fellow. So now, okay, where C is cos theta, sin theta, cos theta is like the transmittivity and sin theta is the reflectivity of the beam splitter. And then, so now you can do all this partial trace calculations. So you have A mode is nothing but trace B of rho C, which is rho AB of this original thing is defined through a thermal parameter kappa. Now you can fix these two entries, the energy basically for a given pair of kappa and transmittivity theta, whatever. So if you fix this thing, so basically the idea is if you take this two-mode state, in scenario one, you only send this portion.
In scenario 2, you retain, the B part, but send the A part, and then check for the, illumination distinguishability. So that is our goal. So using all this, whatever formulas which you have borrowed from ordinate paper and the Dan's original work, whatever, you plug in all those things, and we are able to, calculate out the error bounds on the error probability for in the n copy limit, say between this row AB versus, see, this row C versus only row A being sent. Okay. What we find is, interestingly, so you forget about these two graphs. So, so basically, what we do is, so the first place, one, for instance, plots, logarithmic on the error bounds for the pair, phi n of row A and phi n of row ground. Two plots the same for, phi n acting on I, on this state versus this state, these two. And here you have set, whatever the gamma means, that gamma was nothing but, setting this energy, or basically whatever energy of rho A to be some constant, that is gamma. Here we have chosen gamma to be 1.5, channel parameter kappa to be 0.5, and the noise parameter to be 5, and number of copies to be 10 power 3. And you can see here, this is, these two graphs, basically this is the lower bound, this is the upper bound. Sorry, this is the lower bound, this is the upper bound, and these two pair, lower and upper bounds for situation 1. And clearly, with increasing n, these error probabilities are lower than the error probabilities in situation 1. Which simply means that you are able to perform the distinguishability between, say for instance, these two states. The error, that creeps in distinguishing these two states is lower as compared to the error that creeps in distinguishing, say, this state versus this state in the n copy limit. That means, obviously, the correlation that is present in this row C kappa A of theta, that means that is the correlation present in this two mode Gaussian state, whose variance matrix is this coupled thing. Note that these off diagonal entries are non-zero. So that it simply means that they are not of the product form. That seems to be playing a role in this improved distinguishability between this pair versus these two pairs versus this pair. Okay, this is the first example. This is just between one mode and two mode, comparing one mode with two modes. So now what we do is, okay, so we thought, okay, we'll go for more higher order examples. So what we did is we constructed a 8-mode state. Sequentially, first you construct, some 3, 4, 5, 6 thermal, then couple them through sequential beam splitters. Then again you append, thermal state this side and that side. Then again you couple them, sequentially through again several beam splitters, all 50-50. 3 pi by 2 and pi by 2 simply mean that they are 50-50 beam splitters. Theta equal to cos theta equal to 1 by root 2. And so on. Basically, so you get an 8-mode state, and the idea is to see this correlated 8-mode state, how to put that to use for the illumination problem. So you have this, Uij basically is a beam splitter which couples I and jth mode, and and any subsystem mode is obtained through partial trace of any one of those, whatever, whichever you want to partial trace, your partial trace, and the remaining is whatever is there in your hand. So now, for example, so if you want to take the 4 mode, row 1 to 4, that fellow's characteristic function is given by this, 4 cross 4, not 4 cross, this 4 mode variance matrix. You can see that all the, off diagonal entries are non-zero, and they are related to the original thermal parameters in this manner. So what we actually have is an 8-mode state, and what I'm flashing here is just the variance matrix of the 4 mode of the 8-mode state. First 4 modes of this 8-mode state. This row out 1 to 8. Okay, so this is so you can imagine the the complexity of what we are handling. So now what is that we want to do? So we want to compare the following. 6 situations. So phi n of rho 1 versus, that means you take only the first mode of the 8 mode, compare it with, through this, row ground vacuum pass through the channel. Then you take, you take the row 1, 2, take phi n tensor I acting on row 1, 2, on the first mode of row 1, 2, compare it with phi n tensor I acting on row ground tensor row 2. Then you take, the 3 mode, channel acts only on the first mode, compare it with row ground which is returned, and the sender is retaining row 2, 3 on his side, and this distinguishability between these two, and so on. So we can now take phi n tensor I row 1, 4 with phi n tensor I, row ground acting on row ground tensor row 2, 2, 4 modes retained together, and so on. And then row 1, 6 versus row ground tensor row 2 versus 2 to 6, and row 1 to 8 versus row ground tensor row 2 to 8. So this means row 2 to 8 modes are retained. Here one more first mode of the 8 modes is being sent. The distinguishability between these two will tell basically whether idea is whether 6 is better than say for instance 4 is better than 1. That is the question. Okay. Okay, so let me go to the other results basically. So yeah, so what we do here is so this subscript simply mean that this 2, 1 simply mean that situation 2 versus situation 1, situation 3 versus situation 1, situation 6 versus situation 3, situation 8 versus situation 4. And so as before, so what again we have set the channel to have equal to 0.1 and equal to 0.5, kappa equal to this thermal parameters were chosen, so, and the sense state was identical in all situations having this variance matrix. And you can see, so 8 obviously seems to be better than 4, and then 6 seems to be better than 3, 3 seems to be better than 1, 2 seems to be better than 1, and so on. And you can see, there's increasing amount of correlation. You take that von Neumann based mutual information. If you calculate between the scent and basically this S of row 1 into plus S of row 2 to 8 minus S of row 1 to 8. That is the kind of correlation. For instance, in scenario 6. So that quantity, if you calculate out, you see that for 8 it is 0.0941. So 8 is and 4 it is lesser. So obviously the higher the correlation, there seems to be the lower and upper bounds, error bounds seem to indicate that improved correlation means improved distinguishability in the illumination problem. Okay, so this example just tells, at least suggests, for some particular noise, for some particular thermal parameter channel, and for input, thermal parameter of this input state some particular choice, and for channel thermal parameter and channel noise. This example simply suggests that increasing correlation means improved distinguishability of the scent and whatever return states. Absence and presence of target are more readily distinguished with increasing correlation between the scent and retained modes. Okay, so now the question is, so obviously now this example suggests that increasing correlation means better distinguishability. So the question is, can improved correlation perform better than, say for instance, 2-mode entanglement? 2-mode entanglement is also a form of correlation. It's also the 2-mode entanglement state is a non-product form. So our goal here is now to see if some classically correlated state can outperform a 2-mode entangled state. Basically, entanglement is there between in scenario 1, there is entanglement between scent and IDER modes. In the second situation, there is correlation between scent and the retained modes. So here, so for the 2-mode squeeze state, we take this 2-mode squeeze thermal state. So basically, so this is the variance matrix of the 2-mode squeeze thermal state, and then we ask for And this state by definition is, we can find when it's entangled for some values of kappa thermal it's entangled and so on. That we can find from whatever I've described earlier initially, using the entanglement criteria for two more states. So what we want to do here is now compare the following four scenarios. So phi n tensor I, rho 1, 2 versus phi n tensor I, rho ground tensor rho 2. Then phi n tensor I, rho tilde 1, 2. The tilde 1, 2 simply means that, so that's a two mode space state. Okay, and versus phi n of rho ground tensor rho tilde 2. And then rho 1, 3 versus rho ground tensor rho 2, 3. Rho 1 to 4 versus rho ground tensor rho 2 to 4 retained. And basically the idea is in all these four situations we have the cent mode state. That means rho 1 of rho tilde 1, 2 is identical to rho 1 of rho 1, 2 and identical to rho 1 of rho 1 to 3 and identical to rho 1 of rho 1 to 4. So the cent mode is identical in all the four situations. Now we want to see if, how does this comparison go about. So what we actually find is, so this is 2 prime. The prime simply means that the entangled state. So with increased, so let us read the caption. So 2 prime, we had this entanglement in 2. What we 2 is this is scenario 2 with entanglement negativity, logarithmic negativity 0.0044. Whereas in 2 prime it was 0.6447. Okay, and we have this initial state we chose. The cent mode was 1.2 to 1.82. As evident, so there is a situation. So this 2 is sort of entangled. It has small amount of entanglement. 4 has no entanglement. The situation 4 is this fellow, which is this rho 1, 4 of whatever was shown in the previous slide, which is this state, this rho 1, 4. This 4, rho 1, 4, compared with this 2 mode squeeze state. So this 4 is able to outperform this 2 mode squeeze state, whose entanglement is some non-zero entanglement is there. But however, what we find is increasing entanglement. Obviously, the entangled state overtakes the 4 mode correlated state, highly correlated between 1 and 2, 3, 4. And you can see here, the correlation, squeeze state correlation is lesser, 4 mode correlation is higher. Here, squeeze state correlation is higher, the 4 mode state is lower. So obviously, again, the moral of the story is that increasing quote-unquote quantum correlation seems to render better distinguishability in the quantum elimination. A problem with increased correlation means improved distinguishability. Okay, so this is so this example sort of your classical correlation is able to overtake here. So 4 is able to overtake 2, but 2 is very weakly entangled. Okay, so the thing is, so now is this all that we could do, or are there situations with more entanglement is there and we are able to still use classical correlated states which outperform more entangled states? So for that we consider you take if we consider this 4 mode state, the only difference is that here we liberate the requirement that we are using 50-50 beam splitters. So we use arbitrary this kind of beam splitters, and the first mode of the cent mode is the 4 modes. The energy or whatever is fixed using this thing. This entity C is d cos for 4 theta plus 1. Fixing theta and 1, you fix the cent mode variance matrix. Cent mode is fixed basically, and then you compare it with this asymmetric 2 mode squeeze thermal state, whose density matrix is this fellow, and then again you choose the diagonal. You do all the transformations. You can choose. If you trace out, the 4 mode variance matrix, that fellow's variance matrix is same as the partial trace of this fellow's two-mode variance matrix, which means the sense state is identical in these two situations. You can ensure that. So now we want to compare as before this four scenario, sigma 1, 2 versus sigma rho ground to sigma 2, rho tilde 1, 2. Rho tilde 1, 2 is this entangled state versus rho ground tensor rho tilde 2, and then sigma 1, 3 versus sigma ground tensor sigma 2, 3, and then sigma 1, 4 versus rho ground tensor sigma 2, 4. And to see if there's an advantage using classical correlated state over bipartite entangled state. So this again, we do the analysis. What we found is, okay, so here again, these two graphs are the important graphs, relevant graphs. So for example, not only these two, so 3 is also able to outperform 2, 1 is also able to outperform 2. The entanglement is 1 in 1 is, for instance, in 2 is 0.1880. But however, 2 prime, you increase entanglement, you increase negativity. It is sort of comparable to the 4-mode correlated state. Okay, the correlation between first mode and the 2, 3, 4 modes. So again, you find that comparable correlations. So the 2 prime is entangled, 4 no entanglement whatsoever, purely classical state. Correlations are similar. The upper and lower error bounds are similar, sort of. And even bipartite correlated state here, sigma 1, 2 is able to overtake a 2-mode entanglement state whose entanglement is non-trivial, 0.1880 negativity. And in this example, okay, so all the variance matrix sent was sent to be diagonal 1.5, 1.5. So we set the channel parameter, whatever. This is all set for some numbers. N is equal to 5.02. The channel parameter was 0.5 and so on. Okay, so we are able to find examples which again increase entanglement and still correlated states are able to perform better. Now again, so we there the noise was here, so the noise was higher. So if you again we set an example, noise is lower. If you reduce the noise, you find what happened. 4 can outperform 2, 1 can outperform 2, 3 can outperform 2. 2 is entangled with increased entanglement. In fact, lower noise in the channel, your correlated state even can outperform a 2-mode entangled state with negativity as large as 0.28. And again, increasing entanglement between central and retained modes. If the correlations are comparable, the upper and lower bounds sort of become comparable. So this is these are the examples. Okay, what suggests that you can construct classically correlated state which outperform quantum states, quantum entangled states, bipartite entangled states with regard to and outperform them with regard to the quantum illumination problem. Okay, so now here whatever we have done in these examples, so we have not taken into account this role of this phase space displacement. So basically, so in the example that Tan et al. Considered in 2008, they're comparing the 2-mode squeezed vacuum, which is not displaced in phase space, with coherent state, which is by definition displacement operator acting on vacuum. So so here so when we take displacements into account, so what happens? So that's what this slide sort of summarizes. So what are the observations? So we note that index of correlation between cent and idler modes, cent and retained modes, is invariant under phase space displacement. This is the first observation. Entanglement between cent and idler modes is invariant under phase space displacement. However, the lower and upper error bounds on the error probability, they are independent of phase space displacement only for the displacement of the retained mode or the idler mode. However, it depends on the displacement in the cent mode. This is very critical for the analysis. Okay, so what we found is states with higher index of correlation between cent and idler modes, overpowering states which are entangled in the cent and idler modes, are readily obtained for small phase space displacements of the cent mode. But what we found is conclusions were ambiguous if you are increasing the displacement. Basically, that means the error probability start to overlap and we are not able to draw any useful conclusion. Okay, so so what we find is, if we increase displacement, will sort of displacement sort of overpowers any advantage we have gained through quantum correlation. At least that is what we think we observed. We thought we observed. Okay, so and now some concluding remarks. So what we have got in hand is multimode states which are purely classical in the sense of the Sudarshan's diagonal representation. No, no bipartite entanglement can be generated whatsoever through the state using only passive devices. By passive devices, we mean beam splitters and phase shifters. You cannot generate entanglement whatsoever using simple devices, passive devices. In contrast, Gaussian entanglement is non-local, non-classical. It is highly non-classical state. Somehow, we are having a situation where purely classical correlated states are sort of outperform entangled states through the quantum illumination problem. So entanglement, correlation, what the outcome is that correlation is useful and can be more useful sometimes than entanglement itself. Yeah, so this work was published in this recent issue of Quantum Information Processing. Yeah, so that is all from my side.
Thank you very much, Professor Solomon. It was very, very, very interesting. Now the panel is open for question.
Yeah, can I ask one question?
Yeah, sure.
Yeah.
Please.
Hi, Professor. Thank you for this interesting talk. So, yeah, basically, I want to understand like the states you are considering, they are generated using this beam splitter mode. So, it is not perfectly it is not perfect entanglement.
No, there is no entanglement whatsoever. So, you take thermal state, vacuum state. Vacuum state means no light. Thermal means take a laser, for instance. You basically thermal background, you take illuminate and you basically destroy sort of all the coherence. You get a thermal state. You just mix them through the beam splitter. Okay, there is no, basically there is no entanglement whatsoever.
Okay, but the correlation is greater than the correlation.
Yeah. So that means, so the correlation, basically what we mean is that mixedness, the state, because of thermalizing, the original, you are mixing with the beam splitter, the thermal state with the ground vacuum. Vacuum is pure state. So let us go to the slide with the thermal state. This, where is, this state. You look at this state. It is highly mixed in the fog basis. You take this kind of a state, you take the vacuum state. This is a zero tensor, zero outer product. You mix them using a beam splitter, which means you produce another state similar to this fellow. Okay.
Okay.
It is not product form. It is not of the product form. It is not rho A tensor rho B. Once you mix it, it cannot be written as rho A tensor rho B, but it can be written as, say, summation Pi rho AI tensor rho BI. It is separable.
Okay. So the entropy of entanglement of this state is it 0?
Yes.
Okay.
There's no entanglement. Entanglement is 0 by definition. Correlation is non-zero. If you look at this quantity, for example, if you take that rho AB, which is rho C, partial trace, to get rho A and rho B, you take this fellow, you will get very high value. It is coming purely from thermalization, purely from mixing fellows.
Okay, so in terms of your quantum illumination, it requires this joint detection. So one.
No, not joint detection. So let me go to the first slide. See, the idea is very simple. So you scenario 2. So you are sending, you are sending a two-mode state. So basically there's a two-mode state. You are sending one part of the A part of the two-mode state. Then basically, so for example, you take a beam splitter, you take a thermal state, couple it through a beam splitter. So from the beam splitter comes two light beams. Okay, this is understood. You retain one arm. One arm you keep, that light you retain with yourself.
The other arm light, whatever comes out, you send it to illuminate. Now, with whatever target is there, suppose target was there, that light reflects back from the target and reaches you. That is taken as this 5. So whatever retain your side, that light, one arm light you are retaining. So that light is available. Now the light that was sent and then reflected back, that is 5 tensor I acting on rho AB is also available. So you have the total, the two things together you have with you. The return light as well as the light in the other arm. Put together, if you ask the distinguishability between, say, this fellow versus this fellow. So if target was absent, only rho B was there. But, you know, so your whatever light you sent was lost into the vacuum, into the whatever universe. What was returned to you was the background thermal. That passing through some channel was returned to you. So you will have some light which is not correlated to what you had retained originally in B, and the channel acted on that fellow, that whatever background. Versus in the target's presence, you have both the lights of the original two-mode thing which you created. One part has just gone to the target and then come back. That's what this means. So you compare this distinguishability with, for instance, this fellow. This is more simplistic. You just take a laser, illuminate or laser or whatever thermal state, illuminate the target, whatever light returns, you have that light. Some light is available. Compare that with target was not, you lost your light out, background came, you know, your whatever, your like your night sky, you know, something came back to you, it's dull. It is not having any light whatsoever. Some light, some thermal background, pass through all this channel noise, whatever. So you know, laser light returned to you, light is there, you know that. Versus the background, your tube light, bulb, everything that is glowing in the background. Some background light is there. You are able to distinguish the two. This is the simplistic scenario 1. That is not what we are doing here. Scenario 2 is basically you're retaining, one part, you're sending only one part of a two-mode thing. You get the point. So for distinguishing that situation, you have the second fellow also with you. But idea is now if rho AB was correlated, rho AB could be entangled. But if rho AB was, you thermalize it and then you mix it and then you correlate it out. That means that index of correlation is non-zero. Then what we find is this distinguishability is better than you're able to perform the distinguishing these two better than, say, for instance, these two. Okay. Is this clear?
Okay, yeah. So like for applications like in quantum radar, so quantum illumination is like seen as a potential application, can be quantum radar, but the drawback is that in quantum illumination, it requires to know a priori the distance of the target so that it can store the retained in a quantum memory. So is it the same problem also in this detection?
Yeah. So all whatever same quantum radar only, except that what examples we are producing is that if you have correlation in the sent and retained modes, you have situations where just the correlation can outperform entanglement between sent and idler modes. If you compare a scenario where AB is entangled with, okay, but you take multi-modes, you take a large multi-mode, you correlate it out. A versus B correlation is higher than A versus B entanglement. A is common, rho A is rho A. That state is same. So you take rho A of 8 modes, rho A of 2 modes, which is entangled. Both sent states are same. But now, rho A versus the remaining 7 modes, highly correlated. But it can outperform, say, rho A versus rho B, rho AB entangled with, non-trivial entanglement, basically. You understand?
Yeah. So basically, the detector will remain the same as the quantum illumination.
Yeah. Same. All whatever problems are there, we'll carry over here. Yeah.
I see. Okay. Thank you.
Yeah.
Thank you very much. I have a small question.
Yes,
you are talking about this correlation. So in the channel noise, so the noise is correlated or noise is uncorrelated?
Noise is thermal noise, basically. So you're acting noise only on the one mode of a two-mode state, of a n-mode state. Basically, this is what we are doing.
Okay, okay.
Only on the n mode. So x is, the other thing is retained as whatever retained, nothing you do. You keep it safe.
Okay, okay.
Noise only acts on the sent mode.
Okay, okay.
Yeah.
Okay. Any other question? If not, then let's thank
I have
Dr.
a few questions. Sorry.
Yeah, yeah, please, please.
Thank you for your talk. My question is, what type of channel did you consider in your calculation? Is it
this is the
depolarizing,
channel.
amplitude,
See, this is called the attenuator channel. So what it does is, so this kappa less than 1 signifies that what is returned to you is fraction of what you send. That means, so suppose you send, say, some milliwatt of laser light, some power you send. So say 1 million photons you sent. This kappa tells that 0.5 tells that only half that fellow came back. Okay. In addition, you got some extra noise from the background. So this is the kind of model. Means you send something, only half of that comes back, half the light. This is understandable, right? You send light through atmosphere, not all what you send comes back. Much of it is scattered. So that is captured by this kappa. And then in addition, so for whatever that would be a channel, you need the noise to have this much at least minimum. In addition to this minimum noise, you have additional noise which comes from the background. So that is why that's why we consider this, it's called a noisy attenuator channel. This is very useful for modeling realistic scenarios.
Okay.
Yeah.
Second question is, what value of squeezing parameter you used in your calculations?
Yeah, that you'll have to check that actual slide. So for various examples, we use various things. For example, here we set R is equal to 0.32 and so on. R is equal to 0.0956. So the first example, it was very small squeezing. We could overtake only small squeezing. Second one, little, so the largest squeezing fellow outperformed 2 prime, outperformed 4. But in the next example,
so this value R is
0.3 versus 0.16 and so on. Yeah.
So this value R is meant for 1 mode squeeze state and 2 mode squeeze state.
No,
right?
no, 2 mode. This is the 2 mode state. 2 mode squeezing. We are applying the 2 mode squeeze state to operator on a 2 mode. This is vacuum. This is a thermal state. So you take a thermal state, couple it to a vacuum, then apply the joint thing on the 2 mode squeeze operator on this thing. Then whatever comes out will have this kind of variance matrix. Okay, the details are there in the paper. Then you calculate out entanglement, negativity, everything you can calculate. So the squeezing that this squeeze parameter S of R, that R is this value 0.16 and 0.3.
It's clear. Could you please give definition of illumination? What is the definition?
Yeah, so that's the first slide. So
yeah,
you're sending. See, the thing is, light is described by rho A, some state. Okay. If target was present, so assume that you are shining a torchlight onto a target. If the target was, you see the target code, and what do you mean we see the thing? So some reflection is there. That reflection is not what you sent. It is some modulated version of what you sent. Correct?
Okay.
This is the thing. So now, if the target was not there, what you got back was the background, some thermal background, and some channel. Channel is basically noise in your ambience that acting on the thermal background. If you are able to distinguish these two, then you know the presence or absence of the target. So this is what we call as illumination. Yes or no?
Thank you.
Yeah.
Thank you very much for these lovely questions. If there is no further question, then let's thank Dr. Solomon for this lovely talk. And also this actually brings an end to today's session. So let me take this opportunity to thank all the speakers for their exciting contributions. And so tomorrow we will meet with a new session and new exciting talks. Thank you very much. Let us close the session now. Thank you.